If you look at a standard flat map of the world, Greenland looks absolutely massive. It appears to be roughly the same size as the entire continent of Africa. But Africa is actually about 14 times larger than Greenland. This visual shows why that happens. You simply cannot take a three-dimensional sphere and flatten it onto a two-dimensional piece of paper without breaking the geometry. The map literally stretches and distorts to make the translation work. Right now, physicists working at the Large Hadron Collider are running into the exact same problem. Only instead of flattening a globe onto a table, they are trying to map the hidden rules of the universe onto our three-dimensional world. When early mapmakers saw a giant Greenland on paper, they didn't assume they discovered a massive new continent. They understood their map was under stress. Today, when a physics equation stretches and breaks, it doesn't automatically mean we have found a mysterious new particle. To understand how these measurements are made, we look at the Large Hadron Collider. This massive machine acts as a highly complex camera, tracking the tiny building blocks of matter after they crash into each other at nearly the speed of light. A specific way of looking at these collisions suggests our three-dimensional world might just be a shadow cast by a deeper, four-dimensional reality. In this view, we are living in the shadow of a much more complex universe. This means our current rulebook for physics, the Standard Model, is essentially our best attempt at a map. It is a shadow map, trying its hardest to represent shapes and events that exist in a higher dimension we can't see directly. So when experimental data does not fit our equations, our first question shouldn't be what new object we have bumped into. We should ask what part of that deeper geometry our map is failing to capture. To test the limits of this map, scientists look for specific, extremely rare events. One of them is a particle decay that happens so infrequently, studying it is like finding a quiet alleyway right off the busiest street in the world. Because this specific decay is so rare, there is almost no background noise to confuse the results. This lack of clutter illuminates a clear path, a highly sensitive corridor where physicists can test the absolute edges of their mathematical map. But inside this quiet corridor, researchers noticed a glaring glitch. The way these particles actually broke apart simply did not match what their math predicted. The numbers were off. The standard reaction to this kind of glitch is to assume something invisible bumped into the experiment. If the math doesn't add up, most scientists assume a brand new, undiscovered particle must be interfering with the results. But automatically inventing a new particle to solve a math glitch is like drawing a sea monster on a map to explain away a torn grid line. It ignores the possibility that the problem is the paper itself. There is a different approach. Instead of guessing at new physical objects, we can look at the geometry of the glitch itself. This diagram shows what happens when scientists look at the shapes of the debris, not just how much of it there is, but the specific angles it takes as it flies away. Just like a hand casting a shadow puppet, complex three-dimensional angles compress down into flat, simple outlines on our detector. When the experiment looked closely at these shapes, they found something remarkable. Matter and antimatter behaved in the exact same way. They both showed the same strange distortion. This is a huge clue. If a rogue, undiscovered particle were causing the error, it would almost certainly treat them differently. A new particle would push one type of matter out of alignment, causing its shadow to look different from the other. But because matter and antimatter acted like perfect twins, the glitch looks less like a physical collision and more like a simple geometric stretch in the map itself. The shape and perfect symmetry of this glitch point toward a projection error. It suggests we need to fix our map rather than populating the world with more imaginary particles. To make their broken equations function despite this geometric stress, physicists have to use a mathematical workaround. Think of this workaround as a math dial. Scientists turn it to stretch the grid over unexplained data bumps. This isn't finding a new particle, it just patches our map, leaving a stretched scar where math was forced to fit reality. This math scar is proof that our model is missing some vital information. It is reacting to a deeper reality that our three-dimensional map simply isn't equipped to draw yet. Moving forward, how do researchers know if they found a real mountain or just a smudge on their map? First, they check if the stress remains even when they completely change their map style. If the exact same geometric stretch shows up no matter how they draw the math, they know they found something real. Second, they look for identically shaped stretches in other quiet hallways of physics. If the same distortion appears in different experiments, they've successfully traced a boundary of the deeper world. These tests help us map exactly where our current understanding falls short, without needing to jump to conclusions. The true universe is likely much richer and more complex than the flat shadows we manage to catch inside our detectors. To truly understand it, we have to treat these strange glitches as evidence of map stress, restraining the urge to invent fictional objects to fill the gaps. By accepting the limits of our shadow map, we can stop inventing fictional continents and finally begin tracing the true multidimensional shape of reality.